Hey guys, today we're going to learn about rational functions. Now we have looked at rational functions before, but today we're going to go more in depth in terms of all of the properties of rational functions. The purpose of this lesson is to be able to get all of the qualities of our rational functions graphs so that eventually we can start putting it on the graph. Today we will not be graphing, but we will be finding all of the information we need in order to be able to put it on a graph. So let's start by reviewing the domain of a rational function. As a reminder, a rational function is when you have a function that looks like a fraction. So in the numerator, you may have some function, and in the denominator, you'll have another. And in order to find the domain, keep in mind that fractions, the denominator can never equal to 0. Therefore, in order to figure out what the domain is, we're going to set the denominator not equal to 0. And that's going to tell me the restriction on my domain. So this is the function that I'm using. We have f of x is equal to x plus 1 over x minus 4. So x minus 4 cannot equal to 0. So that means that x cannot equal to 4. And if you need to, you can always put your domain on a number line so that you can figure out how to write it out in interval notation. We know that 4 is not included, but all the other numbers would be fine. So that means that my domain would be from negative infinity to 4, u4 to infinity. Now over here we have g of x is equal to 3x over x squared minus 4x plus 3. Again, I'm going to set my denominator to not equal to 0. Because this one is a quadratic, we are going to factor in order to figure out what are those x values. X squared minus 4x plus 3 is factored to be x minus 3, x minus 1. And now you set each of those individual factors to not equal to 0. So x cannot equal to 3 or 1. And if I put that on my number line, we have here 1 and 3. These are the numbers that it cannot equal, but everything else would be okay. So my domain is going to be from negative infinity to 1, u 1 to 3, u 3 to infinity. The number lines are helpful because you'll know that the left side is negative infinity, the right side is positive infinity, and all of the shaded sections tell you how many sections you're going to have in the domain. Since I have 3 shaded sections here, I should have 3 sets of intervals. Now for this last one, we have x squared plus 9 cannot equal to 0. Now in this one, we would have to solve for x, but this is not a difference of squares, even though x squared is a perfect square and 9 is a perfect square, but it is not a difference. So I can't factor. But x squared is by itself, so we're going to solve for x the old-fashioned way by isolating it. So we're going to subtract the 9 to both sides. And we get x squared cannot equal to negative 9. But then when I try to square root, this is equal to plus or minus 3i. And what this means is that the denominator, there is no real number that makes the denominator equal to 0. Therefore, I can plug in any number I want down here and I will never get a 0. So my domain is going to be from negative infinity to infinity. These numbers that I just solved for, that x cannot equal to, these are called excluded values. Your excluded values of a rational function are the x's that will give you 0 in the denominator. At the same time, when you have 0 in the denominator, what that means is that we have vertical asymptotes on the graph. So For this question, what is present on the graph of the functions at the values that make the function undefined? For a function to be undefined, that means that the denominator is equal to 0. So, and like I said, that is your vertical asymptotes. As a reminder, a vertical asymptote is a line on the graph, a vertical line, that your graph will never touch. And that's why that x value is excluded. So let's look at these vertical asymptotes and how we know that they exist. So here we have f of x is equal to 1 over x. If you look on the graph, you can see that there is a vertical asymptote here at x is equal to 0. And this is because if you set the denominator to x cannot equal to 0, there's nothing to solve for. That is my excluded value, and that's because of that vertical asymptote. And how we know that there's a vertical asymptote is by these limits. Keep in mind that our limits are used to describe end behavior, but they are also the intended y values of your graph. So if the limit as x is approaching 0, and then you see this little symbol here, this means from the left. So here's the 0. As I'm going towards 0, you see that the graph is going down. So the intended y value is negative infinity. Versus the limit as x is approaching 0, and then this symbol means from the right side, this is the right side of 0, and if I follow my graph, you see how it's going up. So this limit is equal to infinity. Again, these are my intended y values. My graphs are trying to reach either negative infinity or positive infinity. This is a proof that we have a vertical asymptote at x is equal to 0, because the graph starts splitting, and instead of going towards a real number like a point on the graph, it's going to infinity, meaning something is there that's blocking it from going past that number. If we look here on this graph, you'll notice that we have a vertical asymptote here at 2. And again, I know it's at 2 not just from the graph, but because here from my denominator, if I make it not equal to 0 and I solve for x, I get that x cannot equal to 2. That is my excluded value, so that means that I have a vertical asymptote at x is equal to 2. So if I wanted to prove that, that means that the limit as x approaches, this is what my x is trying to get to, which is 2, if it's coming from the left side. The left side you see is going up. So this answer would be infinity. And the limit as x approaches to from the right side, you see that the graph is going down, and that's going to negative infinity. So now, how are we going to find these vertical asymptotes, and what is a hole? So you can see here on this graph, we have a vertical asymptote at x is equal to negative 3. And then we have this empty little dot here. That's called a hole. And it's called a hole because there's nothing there. So that's also a break in continuity there. And another excluded value. So how am I going to get these? Now, just from the graph, like I said, what is the equation of the vertical asymptote? So again, vertical asymptotes are lines, so we need to write them as lines. Since it crosses the x-axis, I look at the x value that it crosses, which is at x is equal to negative 3. And in terms of the hole, right, we have the hole at x is equal to 2. Now, how do we find these if we didn't have the graph? Because the whole purpose is to be able to get this information from just the equation, so then you can put it on the graph. So how we do that is by factoring the function. So let's look at our function here. We're going to factor the numerator. If I factor the numerator, x squared minus x minus 2, that is x minus 2, x plus 1. And the denominator, x squared plus x minus 6, is x plus 3, x minus 2. To simplify, we can cancel out any common factors in the numerator and the denominator. And I get here x plus 1, x plus 3. Whatever is left over in the denominator, that's how you know where you have the vertical asymptote. See, if I set x plus 3 equal to 0, I get x is equal to negative 3. This is my vertical asymptote, you see? Then the factor that canceled out, you see how it was x minus 2. If I set x minus 2, the one that canceled, equal to 0, I get that x is equal to 2. The factor that cancels, that's where you have the whole. So, and as a reminder, what we just did here, I have it all outlined for you here for your notes. So the graph of a rational function will have a whole when a factor of the numerator cancels out with a factor in the denominator. The whole is located at the x value that makes that factor equal to 0. So that's what I did. The one that canceled, I make it equal to 0, and that tells me the location of the whole. The function will have a vertical asymptote when the denominator equals to 0, and it is not a common factor of the numerator. Basically, what was left over in the denominator, that's where you have the vertical asymptote. So now let's just practice doing that. Let's practice finding vertical asymptotes, wholes, and putting it together to figure out the domain of that rational function. So let's look at A. We have x plus 3 over x squared minus 9. Let's factor. The numerator cannot be factored, so it'll stay as x plus 3. But the denominator is a difference of squares, so that's going to be x plus 3, x minus 3. My common factors here will cancel, and I'm left with my simplified rational function of 1 over x minus 3. My vertical asymptote is where the denominator is equal to 0. So that means that x minus 3 is equal to 0, x is equal to 3. That's my vertical asymptote. For the whole, that's your common factor set to 0. Therefore, you have a whole at x is equal to negative 3. Now these numbers here, both the whole and the vertical asymptote are going to affect the domain of your function. These are my excluded values. So we're going to create a number line, put those two numbers, negative 3 and 3. Those are not going to be included. The 3 because that's the vertical asymptote, and the negative 3 because that's the whole, the empty space. So my domain is going to be everything else that's in between. So my domain is going to be from negative infinity to negative 3, u negative 3 to 3, u 3 to infinity. Now let's try that over here. We have g of x is equal to x squared minus 5x plus 4 over x squared plus 3x plus 2. So we need to factor this completely. In the numerator, x squared minus 5x plus 4 is going to be x minus 4, x minus 1. And the denominator would be x plus 2, x plus 1. Nothing ended up canceling. So if nothing cancels, that means that there are no common factors. There is no whole. Just because I have a space does not necessarily mean you're going to have everything. So you have to keep that in mind. But we do have two vertical asymptotes then, because I have two factors left in the denominator. So I'm going to set x plus 2 equal to 0 and x plus 1 equal to 0. And I have my vertical asymptotes at x is equal to negative 2 and here at x is equal to negative 1. Now for my domain. My vertical asymptotes are my excluded values. So here's -2 and -1. These are not included, but everything else is okay. So my domain is going to be from -infinity to -2, u -2 to -1, u -1 to infinity. Over here we have h of x is equal to x squared plus 8x plus 15 over x plus 5. So let's go ahead and factor. In the numerator, that's going to be x plus 5, x plus 3 over x plus 5. Now you see here that the x plus 5's cancel out. And so my simplified rational function is now x plus 3. And if there's nothing left over, either in the numerator or the denominator, that's just a 1. So over 1, which we don't really need to ever write. So x plus 3. In terms of my vertical asymptote, you see how we no longer have a denominator. If we do not have anything left in the denominator, then there is no vertical asymptote. But we did have a factor that canceled. And that factor that canceled, that's where we have a whole. So we subtract the 5, we have a whole at x is equal to -5. Again, this is my excluded value. So we're going to create our number line. The -5 is not included, but everything else is. So my domain would be from -infinity to -5, u -5 to infinity. Now that we've established vertical asymptotes and wholes, let's have a look at horizontal asymptotes. As you can see here, we have x plus 1 over x plus 3. And this is the graph. We have a horizontal asymptote, just like a vertical asymptote at -3, but we have a horizontal, so that's that horizontal line that the graph will never touch. And this is the line y is equal to 1. So my graph here is never going to touch that line. So now these are the limits that we are most familiar with, which is our end behavior limits. Your horizontal asymptotes affect the end behavior of your graph. So the limit as x approaches -infinity, so the left side of my graph, you see how it's not going down forever, it's not going up forever, it's leveling out at that horizontal asymptote. It's trying to reach that particular y value. And remember that your limits are the intended y value. It's trying to get to 1. And it's the same thing for the limit as x approaches positive infinity. My graph is leveling out here at y is equal to 1. It's trying to get to 1. So this is basically a proof of horizontal asymptotes. If your limits, your end behavior limits, equal to a particular number, then we have a horizontal asymptote at that particular number. Now your horizontal asymptotes affect the range of your function because that is that's a y value that is not going to be included. So my range here, it goes down forever, it goes up forever, but it does not touch the 1. So my range is going to be from -infinity to 1, u 1 to infinity. And again, I'm using those parentheses. I forgot to mention this earlier, but I use those parentheses with those numbers because those numbers are not included. But we want to make sure that we include all of the numbers that get really, really close to that number. Now, how do we find horizontal asymptotes? It's not the same as how we find vertical asymptotes. Finding horizontal asymptotes depend on the degree of the numerator and the degree of the denominator. So there are 3 rules that we need to remember. If the degree of the numerator, remember that degree is the highest exponent you see, and in this case, in the numerator. If the degree in the numerator is smaller than the degree of the denominator, so you see here, the degree of the numerator is 1, and the degree of the denominator is 2, 1 is smaller than 2, then we're always going to have a horizontal asymptote at y is equal to 0. Now, if the degrees are equal, you see here how the highest exponent of x is 1, and here is also 1. Then what we do is we take the coefficients that are attached to those x values, and we divide them. 4 divided by 2 is 2. If it was any other numbers, let's say if it was 6 over 2, then it would be 3. So whatever those coefficients are, you divide them. And finally, if the degree of the numerator is larger than the degree of the denominator, so here the degree is 2, here the degree is 1, 2 is larger than 1, then that means that there is no horizontal asymptote. So those are the rules. Now, just so you can understand where these rules come from, the reason why this is that, for example, here in this first one, if I plug in, let's say, any number, let's say 2. If I plug in 2, I would get 1 over 8. If I plug in 3, I get 2 over 9 plus 4, 13. If I plug in 3, if I plug in 4, I would get 3 over 16 plus 4, 20. These fractions are going to keep getting infinitely smaller and smaller, closer and closer to 0. Versus here, if I plug in, let's say, 3, I get 1 over 6. If I plug in 4, I get 16 minus 2, so 14 over 7. If I plug in, I don't know, I'm going to go bigger now. Let's say I plug in 10, I would get 100 minus 2, which is 98 over 13. I can keep going. These numbers are getting bigger and bigger. So that means that nothing is blocking the function from going towards infinity or negative infinity. They're just going to keep increasing. So there is no horizontal asymptote. So that's how that works. Now, how do the holes affect the range? Because when you have a hole on a graph, and I'm just going to go back to this graph here. For the domain, that x value is not included, but this is a coordinate. Like, unlike this line where it's just an x, this is a coordinate. It's 2 comma something. So that particular y value where the hole is will also be excluded from the range. So we need to figure out a way of figuring out what the y value would be. So we're going to figure that out now. So in order to find the range, first we need to determine two things. We need the horizontal asymptote, and then we also need to figure out where the hole is. So let's practice first with figuring out the horizontal asymptote. As you can see here, the degree of the numerator is the same as the degree of the denominator. So the horizontal asymptote is going to be at y equals, and you take the coefficients of the leading terms of the numerator and denominator and you divide. This is 1 over 1, so 1 divided by 1 would be 1. So this means that y is equal to 1 will not be included in the range. Now for the hole, because we need to know what that y value for the hole is. We need to go back to how we find a hole, which is to factor. So my f of x is going to equal to x squared minus 4 is a difference of squares, so x plus 2, x minus 2. X squared plus x minus 6 can be factored to be x plus 3, x minus 2. So my x minus 2's cancel. So that means that I have a hole at x is equal to when this is equal to 0, which is at 2. That's the x value. But for the range, I need the y value. So what we do is we have my simplified rational function is x plus 2, x plus 3. To figure out the y that goes with this x, we're going to take the x and we're going to plug it in. So f of 2 is going to equal to 2 plus 2, which is 4, over 2 plus 3, which is 5. This is the y value of my whole. So the whole is at 2, 4 over 5. This is the value that I need to exclude from the range. So if I do my number line, we have 1 that I need to exclude and 4 over 5. So I'm going to put those both on my number line. These two values will not be included, but everything else will be included. So my range is from negative infinity to 4 over 5. U 4 over 5 to 1. U 1 to infinity. Let's try that with this one here. We have 2x squared plus 12x plus 10 over x squared plus 3x plus 2. Let's first find the horizontal asymptote. So I know at least one of my values that I need to exclude from my range. The degree of the numerator is the same as the degree of the denominator. Therefore, my horizontal asymptote is when I take those coefficients and divide them. 2 divided by 1 is 2. So this is one of my excluded values. Now to get the excluded value if there's a whole, I'm going to need to factor. In the numerator, I can take out a 2. So this would give me 2x squared plus 6x plus 5 over x squared plus 3x plus 2. Now let's factor that completely. We have the 2. X squared plus 6x plus 5 is x plus 5, x plus 1, over x squared plus 3x plus 2 is x plus 2, x plus 1. Here, the x plus 1's cancel. So that means that there is a whole at x is equal to negative 1. Since again, that's where this factor would equal to 0. My simplified rational function is 2x plus 5 over x plus 2. To figure out the y value, I need to plug in that negative 1. So f of negative 1 is going to equal to 2. Negative 1 plus 5 is 4 over negative 1 plus 2, which is 1. And this is going to equal to 8. So the whole is at the coordinate negative 1, 8. This is my second excluded value for the range. So I can put that on my number line. I need to exclude the 2 and the 8. These two numbers will not be included, but everything else will. So my range is going to be from negative infinity to 2, u 2 to 8. Oops, I put infinity there. And then u 8 to infinity. Now what we're going to do is we're going to put everything together. This is all of the information that we can get just from the equation. We can get the equation of the vertical asymptote, the whole, the horizontal asymptote, and the domain and range. The order in which you get all this information is completely up to you. I'm just going to go in order of however I feel like it. So for the first one, we have f of x is equal to x squared minus 2x minus 3 over x minus 2. The first thing that I kind of like to look at is my horizontal asymptote, since I don't need to do anything to my function to figure out where I have a horizontal asymptote. All I have to do is compare the degree of the numerator with the degree of the denominator. The degree of the numerator here is 2, whereas here it's 1. Since 2 is greater than 1, that means that there is no horizontal asymptote. Keep in mind, for horizontal asymptotes, if the degree is greater, there is none in the numerator. If the degree is smaller in the numerator, then it's y is equal to 0. And if the degrees are equal, we divide those coefficients. So I already know no horizontal asymptote. Now I know that I can get the rest of the information by factoring my function. So I'm going to go ahead and factor. X squared minus 2x minus 3 is x minus 3, x plus 1. And this is over x minus 2. Since nothing cancels out here, I know that there is no whole either. But I still have a factor in the denominator, so if I make that factor equal to 0, that's going to tell me where I have a vertical asymptote. So I have a vertical asymptote here at x is equal to 2. Now for my domain. My domain is restricted by the vertical asymptote and if I had any holes, but I don't. So my domain is going to be all of the numbers except for the 2. So my domain is x is equal, oops, that's not my domain. My domain would be from negative infinity to 2, u 2 to infinity. Now my range is affected by any horizontal asymptote and the y value of the hole. Since I have no horizontal asymptote and no hole, that means that there is no restriction on the range, so my range is going to be negative infinity to infinity. Now let's have a look at this function. I'm going to get my horizontal asymptote first, since I don't have to do anything here, so I compare the degrees. The degree here is 2, and this one is 2, so since they're equal, I'm going to divide those coefficients. 2 divided by 1, I get the horizontal asymptote at y is equal to 2. And keep in mind that all of our asymptotes are lines. You need to make sure that you write the equation as a line, not just the number. To get the rest of the information, I know I'm going to have to factor. So I'm going to factor my numerator. From all of these terms, I can divide out a 2. So I get x squared minus 2x minus 8 over x squared minus 4x minus 12 can be factored to be x minus 6, x plus 2. If I factor completely, I get 2, x squared minus 2x minus 8 is x minus 4, x plus 2, over x minus 6, x plus 2. These are my common factors, so I can cancel them. And since I just canceled out, I know that that is the location of my hole. So I have a hole. Now when we're writing out the holes, you're going to write out the coordinate. I know that my x value of the coordinate of the hole is at negative 2. So what do I have left here? My simplified rational function is 2 x minus 4 over x minus 6. I need this y value of my hole, so I'm going to go ahead and plug in the negative 2. If I plug in negative 2 minus 4 is negative 6, and negative 6 times 2 is negative 12, over negative 2 minus 6 is negative 8. And this can be simplified. Negative over negative will become positive. And 12 over 8 can be simplified by 4, which will give me 3 over 2. So that's the coordinate of my hole. Now my vertical asymptote can be found by setting the denominator equal to 0. If x minus 6 is equal to 0, that means I have a vertical asymptote at x is equal to 6. Now that I have these 3 pieces of information, I am good to write out my domain and the range. For my domain is restricted by both the vertical asymptote and the x value of the whole. So my x value is smaller there, so -2 and then 6. These are excluded, but all of these other numbers are okay. So my domain would be from -infinity to -2, u -2 to 6, u 6 to infinity. Now my range is affected by the y value of the whole and the horizontal asymptote. 3/2 is 1.5, so that's smaller than 2. These are my numbers that I'm going to exclude, but everything else is fine. So my range would be from -infinity to 3/2, u 3/2 to 2, u 2 to infinity. For this last one, we have f of x is equal to x minus 1 over 3x squared minus 12x plus 9. I'm going to compare the degree of the numerator with the degree of the denominator so I can get my horizontal asymptote. Since the degree of the numerator is 1 and the degree of the denominator is 2, 1 is smaller than 2, therefore I have a horizontal asymptote at y is equal to 0. To get the rest, I'm going to factor. So f of x is going to equal to x minus 1 over, here I can take out a 3, and I get x squared minus 4x plus 3. I can now continue to factor, and that would give me x minus 1 over 3, x minus 1, x minus 3. My x minus 1s will cancel. Since I just canceled, that means that I have a whole where that factor is equal to 0, which is at 1. Now, sorry, we're going to write out the coordinate. So that is the x value of my whole. Now to get the y value of the whole, my function is my simplified rational function. Since there's nothing left in the numerator, we're going to put a 1 over 3 times x minus 3. Since my x value is 1, I'm going to take the 1 and plug it into my function. So that is 1 over 3 times 1 minus 3, which is -2. And 3 times -2 is -1 over 6. So that is the y value of my whole. In the denominator, I still have an x minus 3 as a factor, so my vertical asymptote is going to be at x is equal to 3, since again, that's where this factor would equal to 0. For the domain is affected by both the x value of the whole and the vertical asymptote. So 1 and 3 are my values that I will exclude. So my domain is going to be these 3 sections. So from -infinity to 1, u 1 to 3, u 3 to infinity. My range is affected by the y value of the whole and the horizontal asymptote. So -1 over 6 and 0 are my excluded values for the range. But everything else is allowed. So my range is going to be -infinity to -1 over 6, u -1 over 6 to 0, u 0 to infinity. And that's how you find all the vertical asymptotes, horizontal asymptotes, wholes, domain, and range for rational functions.